1.5, absolute value equations and absolute value inequalities. And there's a very big difference. So remember, equations will have equal signs, inequalities will be our less than or greater than symbols. So to start off, let's talk about absolute value equations. So remember, if I told you to find the absolute value of 7 and the absolute value of 7, your answers would both be 7 here. Okay, so if I'm trying to figure out what the absolute value of x is, there's two possible values, right? The absolute value of 7, you could have either, you could have either started with -7 or a 7. So for instance here, whatever we have in the absolute value, like we're trying to figure out what x could be so that if we take the absolute value of it, we'd get 10. Well, there's two different options. X could either be a positive 10 or x could be a negative 10, right? Because if you take the absolute value of -10, you get 10, and if you take the absolute value of 10, you'd also get 10. Okay, so we always have two solutions, or typically have two solutions when we're dealing with absolute values. The absolute value of x equals 0, so you're trying to figure out what numbers could you plug in for x, and when you take the absolute value, you get 0. Well, there's not a negative version of 0. There's only one possible answer that you could plug in here, and it would be 0. The absolute value of 0 is the only number that would give you 0. And part C says the absolute value of x equals -1. Is there a number that you could plug in for x when you take the absolute value, you'd get a -1? No, absolutely not. Absolute value, you never get a negative. So this is a no solution case, right? If I plugged in -1 and I took the absolute value, I'd get a positive 1. If I plugged in the absolute value of 1, I'd also get a positive 1. I will never, ever, ever get a negative after an absolute value. So this is a no solution. Okay, checking whether a value is a solution to the equation. So it says the absolute value of 4x plus 5 equals 10. And let's see if x equals -3 is a solution. We need to check and see if it works. So we're plugging in -3 in for x and solving and seeing question mark, is it equal to 10? I don't know yet. So in my absolute value, I'm going to have -12 plus 5, which would be -7 absolute value. And the absolute value of -7 is 7. So 7 does not equal 10. So no, this is not a solution. -3 is not a solution. Let's check and see. Actually, I want you to pause the video. Is W equals 4 a solution to this inequality, or sorry, absolute value equation? Okay, hopefully you found out that it was a solution. When you plugged in 4, you took 4 times 2 and got 8. 6 minus 8 is -2, but the absolute value of -2 is just 2. So 2 equals 2 on the other side. This would be a solution. All right, solve the equations for me, C and D. Remember on the previous slide, I did a few for you. See what you come up with for what x equals here, and if x equals anything on part D. So for part C, you should have found out that one solution could be 16. If you plug in 16, take the absolute value, you would get 16. And the other solution is -16. If you plug in -16, take the absolute value, you'd get 16. In part D, this one's a no solution because there's no number that I could plug in, and when I take the absolute value, I get -45. Anytime you have absolute value equal to a negative number, it's going to be no solution. Okay, so let's actually solve absolute value equations now. So in the last slide, we checked whether values were solutions. Let's figure out what value for x would actually be a solution here. So to do this, we need to think about this part in my parentheses, the 3x plus 4. what would it have to simplify to or come down to or equal in order for you, when you took the absolute value of it, to be 10? Well, one option is if it was just 10 itself. So if 3x plus 4 equaled 10, then I would be okay. Right? If this part equals 10 and I took the absolute value, it would equal 10. The other thing that it could be is if this part was negative 10 and I took the absolute value, then it would equal 10. So there's two options. If 3x plus 4 equals 10 and if 3x plus 4 equals negative 10, you'd still come out with a true equation. Both of these would give you 10. So anytime we have this type of problem, an absolute value problem, an absolute value equation, we need to set up two different equations. Okay, one's positive and one's negative version. Okay, 10 over here is positive, 10 over here is negative. So let's solve each of them individually like we would any other equation. Subtract 4 on both sides. And then divide by 3. And we get x equals 2 for one of our solutions, right? If I plugged in 2 here, this would give me 10 and give me the absolute value of 10, which does equal 10. Over here, same thing, solve for x, so subtract 4. Negative 10 minus 4 is negative 14. Divide by 3. And I get x equals negative 14 over 3. I like to teach people that it's kind of silly, but it works for some people, that the absolute values mean you're in prison, these absolute value bars. You're behind bars, you're in prison. So to escape prison, so for 3x plus 4 to escape prison, he needs two plans, right? He needs a plan A to escape and needs a plan B. So anytime you have an absolute value equation or you're in prison, you need a plan A and a plan B. That's where the two equations come from. Plan A is you try to escape by your normal identity. Plan B is you change your shirt, so you change to negative. Like I said, it's silly, but it works for some people. If you're in prison, you need a plan A and a plan B to escape. There's the normal identity route, and then you change your shirt for the plan B. Okay, let's look at number B down here. I have the absolute value of 2x minus 1 plus 3 equals 8. So I am in prison, right? X, the value of X is in jail. And for him to escape, he needs a plan A and a plan B. However, he has no chance of escaping because there's a guard here. This plus 3 is guarding the gate, so we need to get rid of him. So we need to subtract him out of the way, get this guard out of our sight. That way we have a chance to actually escape. So these guys cancel. 8 minus 3 is 5. And I still have my absolute value of 2x minus 1 over here. So x is still in jail. Now he's ready to escape. All the guards are gone. So I need a plan A and a plan B. Plan A, everything stays the exact same. 2x minus 1 equals 5. Plan B is you have to change your shirt. So 2x minus 1 equals a negative 5. Okay, a positive and a negative, two equations. So one thing I want you to remember is on these types of problems, you first need to get the absolute value by itself, right? We got rid of the guard. We need to get absolute value all by itself. So now we're ready to solve our two equations. So to solve for x, we're going to add 1 and then divide by 2. Okay, so that could be one of our equations, or sorry, one of our solutions, or the other solution could be -2. All right, there's two possible answers, two numbers that you could plug into the original equation for x, and you'd get 8. One number is 3, the other number is -2. Okay, so a plan A and a plan B when you have absolute value equations. All right, I want you to give it a go on A, part A. Something I want to remind you of, when you have the absolute value equal to 0, you're only going to have one equation. Okay, so on this one, be aware of that. Make sure, since this has a little star around it, that star stood for you get the absolute value by itself first. So get the absolute value by itself, and then try to escape x out of jail. All right, so hopefully you knew to get the absolute value by itself, so you're going to subtract 4 and cancel these out. But 4 take away 4 is 0. So I have the absolute value of x minus 2 over 5 equal to 0. So we're in jail, we need a plan A and a plan B, but because it equals 0, there's only one value that this absolute value could be for it to equal 0, and that'd be 0, right? If this whole thing, x minus 2 over 5 equaled 0, that's our plan A. There is actually no other plan B on this one. Okay, so if you have it equal to 0, you only have one plan. So we're going to get x by itself, and to do that, you may or may not see, but there are hidden parentheses around the numerator. Okay, so we have to get the 5 away before we get anything else away from x. So it's being divided by 5, so we want to times by 5 on both sides. We cancel out that, and then we're left with x minus 2 equals 0, because 0 times 5 is 5, or 0. Then I'm ready to add 2, and my final answer is x equals 2. So there's only one number, the number 2, which I could plug in here and simplify this down, and it would give me 4. Right? 2 minus 2 is 0. 0 divided by 5 is 0. The absolute value of 0 is 0, so 4 equals 4. Yeah, this is my only solution. The next one, part B, I want you to notice that there's 2 guards. Okay, we're in jail, but we can't escape jail until we get the absolute value by itself. So there's a guard over here by the gate, and there's a guard watching the jail cell. Okay, so we're going to get rid of the guard by the gate if we're going to have any chance to escape. Okay, we need to get rid of this guy in the watchtower first. So we're going to add 6, drop down the 2 times absolute value of 4 minus 3x. -2 plus 6 is 4. Now that we got rid of the guy in the watchtower, we need to get rid of the guy by the jail cell. So this 2 is being multiplied by the absolute value, and to undo multiplication, we need to divide. If we do it on one side, we have to do it on the other. So then it comes down to the absolute value of 4 minus 3x equal to 2. Now that my absolute value is by itself, I'm ready to set up a plan A and a plan B. Plan A is everything stays the same, 4 minus 3x equal to 2. Plan B is we have to change our shirt, so 2 would become negative. Okay, Okay, there's a reason I didn't have a plan B up here is because there's no negative value for 0. So now I'm going to solve. Need to get x by itself. Okay, so we always want to undo the addition and subtraction first. Keep in mind this is a positive 4, so we need to subtract 4 in order to undo it. Drop down the negative 3x, and 2 take away 4 is negative 2. Then I'm ready to divide by negative 3, and x equals negative divided by negative is a positive 2/3. Plan B we need to solve. So again, I'm going to subtract 4. Drop down my negative 3x. Negative 2, take away 4 is negative 6. And divide by negative 3. Because x is being multiplied by negative 3, so I divided, and I get x equals a positive 2. So one value could be 2/3, another value could be 2. Both would work in this equation. Okay, one more type of absolute value equations that you're going to see is when it involves two absolute values equal to each other. Okay, when this happens, we do the same thing we did with our absolute value equations. We're going to have a plan A and a plan B. Okay, remember plan A, everything stays the same. So 3x minus 4 equals 7x minus 16. Plan B, remember in all of our other plan Bs, we changed the shirt. We changed this side negative in plan B. So that's what we're going to do for plan B. So the left side stays 3x minus 4. And the right side, we have to negate it. But we're not just negating the 7x, right? We're also negating the negative 16. So I like to put my negative out in front and put parentheses around the right side. That way, I remember to distribute this negative because I'm changing the sign of both of them. This would become negative 7x, and a negative times a negative, this would change to a positive 16. And then I'm ready to solve just like any other equation. I'm going to try to move my x over here to the left, so I'm going to add 7x. That way I can combine it with the 3x and get 10x minus 4 equals 16. Now that my x's are combined, I want to move my numbers to the right side. So I'm going to add 4. And lastly, divide by 10. And I get x equals 2. However, we still have plan A. So I can subtract 7x if I want, but I'm going to subtract 3x because then my x value will stay positive. So I have negative 4 equal to 4x minus 16. The x's are combined, so I need to move the numbers to the other side. I'm going to add the 16. Negative 4 plus 16 would be 12. Last step is to divide by 4, and I get x equals 3. So x could either be 3 or x could be 2. All right, part B. I want you to try and set it up yourself. This one is kind of tricky because it's a little bit of a special case, but see how far you can get. Okay, plan A, everything should have stayed the same. So x plus 5 equals 11, or x plus 11. Plan B should have been x plus 5 equals negative x plus 11. So when you go to solve this and you're trying to combine like terms and you subtract x on both sides, these x's cancel, but these x's also cancel. So you're left with 5 equals 11, which is not true. So this is going to not give you a solution. Okay, so the positive version won't give you a solution, but let's see if the negative version will. So we need to distribute our negative, making this negative x minus 11 and x plus 5 on the left side. So I want to move this x over by adding, and then I get x plus x is 2x plus 5 equals negative 11. Move my 5 over by subtracting. Negative 11 minus 5 is negative 16, so I'm going to divide by 2, which leaves me with x equals negative 8. So there's one answer here. The only number that you could plug in for x and both sides be equal is the number negative 8. Okay, changing it up a little bit. We have absolute value inequalities now. Inequalities, remember, are greater than or less than symbols. So this says the absolute value of x is less than 3. So let's think about it graphically. What numbers could we plug in for x whose absolute value is less than 3? Well, let's just start with 4. Could we plug in the absolute value of 4 and this be true? No, because the absolute value of 4 is 4 and 4 is not less than 3. Okay, so we don't want 4. 1, 2, 3, 4. And we could try 5, 6, and 7 if we wanted, but same result, right? Those would not be true. Let's try and plug in 3. If we plugged in 3, I'd get the absolute value of 3 is less than 3. The absolute value of 3 is 3. Is 3 less than 3? No, it's not. It's equal to. So 3 wouldn't be a solution. What about 2? The absolute value of 2 would be 2, and 2 is less than 3. So 2 would work. Okay, that's good. Same thing for 1, right? If I plugged in 1, I'd get 1 is less than 3. And same thing if I plugged in zeros. Absolute value of 0 is 0, and that'd be good. Now let's look at negatives. Okay, let's say I plugged in negative 1. The absolute value of negative 1, is that less than 3? Yeah, because that'd be 1 is less than 3. That's good. Negative 2. Sure, the absolute value of negative 2 is 2, and 2 is less than 3. What about negative 3? No, because 3 isn't less than 3. So negative 3 wouldn't be a solution. And neither would negative 4. If I plugged in negative 4 here, the absolute value would be positive 4, and 4 is not less than 3. So just thinking about it that way, kind of guessing and checking, it looks like those solutions are going to be right in here. Okay. So one thing I want you to remember from last section is that the less than symbol was an open circle, and 3 is our endpoint. So we're going to have an open circle at 3 or a parenthesis, or sorry, that's negative 3, at 3, but also at negative 3. They look like they could be our boundaries, right? If I plugged in negative 3, it didn't work, but if I plugged in negative 2.999 in the absolute value, I'd get 2.999, which is still less than 3. Okay, so I want everything in between these two endpoints. So in algebraic terms, what does this graph look like? Well, it looks like this bounded inequality where negative 3 is an endpoint, positive 3 is an endpoint. I have an open circle. And x values need to be greater than negative 3, but also less than 3. So those values are in between here. So this pattern for less than absolute value inequalities, right? This was a less than, will always hold. Okay, and it's true for less than or equal to also. Any less than absolute value inequality has this pattern. Then if the absolute value is less than a number a, then you take the negative version of a, put the less than symbol, put whatever was in your absolute value, here it's x, put the less than symbol, and then the positive version of your endpoint. Okay, just like we did up here to get this. Whatever's in your absolute value goes in the middle. You have the two less thans, and then you take your number, do a negative version and a positive version on the right. So what I want you to think when you see a less than symbol, think and, less than. Okay. Why am I thinking and? Where does and come from? Well, this is an and inequality, right? It's not an or, that's an and we talked about that in the last section. Okay, so let's look at an example so we can see what I'm talking about here. Sometimes it won't just be x in the absolute value. So for instance, I have x minus 5 is less than 2. So I see it less than, I'm making an and inequality. I'm making a bounded inequality where I take the negative value, I put the less than symbol. If this was a less than or equal to, I put a less than or equal to. I put whatever was in my absolute value, and then another less than symbol, and then the positive value of 2. Okay, so I've created an and inequality, and now I have to solve it. So we worked on solving these last section, so I need to add 5, but I'm going to add it in all 3 places so that I'm left with x is less than 7, but x is greater than 3. That's something that I can come over here and graph. Let's make this 5, 6, 7, 4, 3, 2. So I know I have an open circle at 3, an open circle at 7, and it's an and ands go in. Ands go in. Less than 7 but greater than 3 are these numbers right here. Okay, let's look at one that's not less than. Okay, so this only works for less than. Let's look at a greater than. X, absolute value of x is greater than 2. So let's think about it graphically. What values could you plug in for x and you take the absolute value and they're going to be bigger than 2? Well, let's just start with 0. The absolute value of 0, that is not going to be bigger than 2. So 0 won't be a solution. Okay, let's try 1. Is the absolute value of 1 bigger than 2? No, the absolute value of 1 is 1. So 1 won't be a solution. What about 2? The absolute value of 2 is 2. 2 is not bigger than 2. That wouldn't be a solution. Let's try 3. The absolute value of 3 is 3. So 3 is bigger than 2. So all right, there is a solution. 1, 2, 3. 3 is a solution. Let's keep going just to see if 4 would be. The absolute value of 4 is 4. 4 is bigger than 2, so that would be a solution. And it would keep going, right? For 5, for 6, for 7, and almost like anything up to 100 or 1,000 or 1,000,000. So let's work our way back. We started at 0. Let's try -1 now. The absolute value of -1 is +1, and 1 is not bigger than 2, so that wouldn't be 1. -2, no, because 2 isn't bigger than 2. Let's try -3. The absolute value of negative 3 is positive 3. So yeah, 3 is bigger than 3. So negative 3 would be a solution. Just for fun, let's try negative 4. The absolute value of negative 4 is positive 4, so negative 4 would be a solution. So negative 5, negative 6, you need to keep going, right? So this looks like something that we've graphed before. What I want you to notice is the greater than symbol at 2. So we want to, at 2, put an open circle, and at negative 2, put an open circle. Okay, these are our boundaries. And it looks like since all of these were solutions, my arrow needs to go and grab all of them, and my arrow over here needs to go and grab all of these solutions. Okay, so this is a pattern, right? If I were to ask you guys what's the inequality that represents this graph, you would say, well, looks like x, the values on this red line, are less than negative 2, or the x values over here could be greater than 2. So this pattern for greater than absolute value inequalities always holds. Okay? Given the inequality, the absolute value of whatever's in your absolute value is greater than a, you can always form an OR inequality. So the first one, the first part of your OR is the x, or whatever's in your absolute value, is less than the negative a, so the negative version of a, or x is greater than, that's supposed to say a, the positive version of a. Okay, so greater than a, that stays almost exactly the same, but the first part of the OR, you have to flip the symbol and make it negative. So ORs are a little tricky. So here's what I want you to remember. This is how I remember it. Great or than make an OR inequality. Okay, so we have less than is an AND inequality where it's smushed. Great or is an OR inequality where you have two different parts. So let's look at this example. X plus 6 is greater than 10. It's a greater than problem. So I need to make two different ORs. Let's start with the easy one. You take whatever's in your absolute value, and you take your greater than symbol, and you take whatever's on the other side of that symbol. Everything stays the same. Okay, that's one. The other one is whatever's in our absolute value stays the same, x plus 6, but then I need to change greater than to less than and change the 10 to negative. Those are my two different inequalities. Those are my ORs that I'm going to be solving. So I'd subtract 6 here. Remember, an OR inequality, you treat them separately. And I get x is less than negative 16. This one I'm going to subtract 6 also. And I get x is greater than 4. Remember, ORs go out on the graph. Let's see, how could I do this? Let's just call this negative 16, and let's call this 4. I know it's not accurate, but I don't think I gave you a long enough number line. So at both of these, I'm going to have open circles, right? Because it's not an or equal to. You could also use parentheses if there's an open circle. X numbers that are greater than 4 are those numbers over here. Numbers that are less than negative 16 are those numbers over here. ORs go out. Okay, ORs go out. Ands are going to go in, right? And that's why we went in between on that and we went out on this or. Okay, on this last slide, something I want to point out to make you aware of is notice how this is an absolute value is less than -1. Is there any absolute value that's ever going to be less than -1? No, because absolute values always come out positive, right? So you're never going to have a positive number that's less than -1. So if you have an absolute value is less than any negative number, this is a no solution case. Okay, when the absolute value is less than a negative, it's always no solution. All right, and the other thing that you might come across is this is an absolute value in an inequality, but before you can treat it as a greater than or a less than problem, right? A greater or less than, you need to get the absolute value by itself, just like we were doing with the equations where you couldn't get out of jail till you got the guards away. So to get this guard away, you're going to have to multiply by 2. And then you're left with absolute value of x plus 6 is greater than or equal to 32. Okay, at this point, I want you to pause the video. This is a great or, so see if you can set up a great or than problem. All right, one of the equations that you should have set up is keep everything the same. X plus 6 is greater than or equal to 32. The other one you should have set up was x plus 6 stays the same, but you need to flip the direction of the inequality and change 32 to negative. So you're going to solve both of them. And you get x is less than or equal to negative 38, or x is greater than or equal to 28. So what's that look like on the graph? Well, here's negative 38, here's positive 28. Ors are going to go out, but just to be sure, I want x values greater than 28, so it's an or equal to. My circle gets filled in. The numbers bigger than 28 are to the right. X is less than or equal to 38. So again, it's filled in. The numbers less than are in this direction. Please, if you have any questions, don't hesitate to ask. Just know the difference on the problems that are inequalities and the problems that are equations.